We're going to continue working with conic sections. The next one we're going to work with is an ellipse. So an ellipse is actually kind of an oval in shape with two special points on the inside. These points are called foci. And here it's demonstrated with an orbit as an example. So as a planet orbits the sun or as a comet orbits the sun, it's going to have an elliptical shaped path quite often. And that ellipse is going to have the sun at one focus. Now, half of the distance along the major axis is called the semi-major axis. We're going to need to pay attention to that distance for later on, section 10.6 mostly. But you can find these points on an ellipse by using these equations. C squared is A squared minus B squared, or vice versa, whichever one is positive. That's assuming that your ellipse has a form and its equation something like this: x minus h squared over a squared plus y minus k squared over b squared, and that's equal to 1. If your ellipse is in that form, then it's going to have a center at h and k. And you can find its foci a distance of c away from the center along the major axis. Now, the major axis is the longer of these two. A and B have to have different lengths, because if they have the same length, then basically you're going to have a circle. So give you a moment or two to jot that down. And you can jot that down while I get up our little demonstration that talks about this. So that's going to be the Desmos link that I put in the chat. So, all right, so that link takes you to this page right here. And the cool thing here is that I've got a nicely drawn ellipse. It doesn't really look dramatically oval, but we can make it look more oval by adjusting this slider. Now, I kept the denominator of my x squared term fixed, but I can adjust the denominator for b squared. And as I do, can you notice what's happening? It's kind of flattening a little bit, actually a lot. And the more you flatten it, the more eccentric it's going to become. And the eccentricity is really going to be a ratio of two things. It's going to be a ratio of c, distance from the center to your foci, and A, which is your major axis. So that distance there. Now, Earth and all the other rocky planets have an elliptical orbit, but the shape of the ellipse is not really that far away from being a circle. In fact, most people would look at something like this and say, oh, well, that's like pretty much a circle, isn't it? And it looks very close to a circle. You're right, but it's not quite a circle. I'd have to go all the way here to get a circle. Now, Earth's eccentricity is just, I don't know, it's even less than that. It's like 0.016. So it really takes some inspired observation to notice that we don't travel around the sun in a circular path, as was thought for a long time by some of the braver earlier astronomers like Nikolai Copernicus. One other thing here that I want to point out, watch what happens to the foci as the ellipse returns to more and more of a circular shape. Foci are getting closer and closer together, closer and closer to the center, and finally, bam, what happens? When this is a perfect circle, you really have one focus, which is the center of your circle. So the circle is kind of a special case of an ellipse. All right, where did you see the shape of an ellipse other than planetary orbits? Good question. let's continue to view our little slideshow. Here's some properties of an ellipse. Ellipses have an acoustical property where if you're standing at one focus and you speak, then your voice is going to be reflected as somebody standing at the other focus. There's an ellipse in front of the Capitol building, the White House. Sun is at one center or one focus of our elliptical path around the sun. And we're actually farther away from the sun now than we would be in winter. Kepler was the first one to notice that we travel around the sun in an elliptical shape. Lithotripters are amazing. I'm going to skip through those. There's a lot of cool shapes using ellipses. There's an elliptical shaped dome inside the Capitol building. And then that takes us to hyperbolas. Let's get busy though graphing ellipses. And the first one we're going to work with is this one right here. Now, if you've not seen ellipses before, a good place to start graphing this would be by, say, setting x equal to 0 to get the y-intercepts. Now, if I set x equal to 0, that gives me y squared over 25 equals 1. So y squared equals 25, or y is plus or minus 5. So when x is 0, y is 5 or negative 5. And you can play the same game with setting y equal to 0 to get the x-intercepts. And what you'll find is you end up with 4 and negative 4. And these points happen to be the vertices of our ellipse. So let me graph those. I don't know if you noticed, but on the y-axis, these are tick marks are scaled by 2. So I got 0, 5, 0, negative 5. Likewise, on the x-axis, things are in a scale of 2. So 4 and negative 4. And now you get to play a college-educated version of connect the dots. So we want to connect this in a smooth way. So
Could you go back up to that equation you wrote on the top for a second?
this one?
Yeah.
All right. So hopefully your ellipse is a little bit smoother than mine. I drew mine in a touch of a hurry. The only thing I object to in an ellipse is when people connect them kind of like a third grader and just draw straight lines there. It's not going to have a diamond shape. These are going to be smooth curves that will be differentiable, you know, assuming that you had a function there. So just don't draw a diamond and we'll be fine. Now there's two axes that run through here. The longer of the two is your major axis. The shorter of the two, of course, would be your minor axis. Now it's along the major axis that you're going to find your foci, and that's where we're going to use the formula c squared equals b squared minus a squared. Just basically subtract the square of these things in the order that makes sense. Now, before I do that, let me take and reorder this or rewrite this a little bit, because the way we found the vertices is a little bit tedious. Setting x equals 0, setting y equals 0. There's a little bit of a shortcut that you might be able to pick up on if you notice that you can write both of these denominators like this, 5 squared and 4 squared. And then in the y direction, to find the vertices, you move up 5 and down 5. And in the x direction, to the right 4 and to the left 4. So there's your a squared and b squared. And if I do c squared equals 5 squared minus 4 squared, I end up with c squared is 9. So c equals plus or minus 3. And that's going to help me find my foci, which are going to be 3 away from the center along the major axis. All right. Let's do a couple other examples. Are these familiar to you guys? Do you need a lot of examples to get back up to speed, or is it kind of like, oh yeah, this is coming back quick?
What exactly is C?
C is this distance here that helps you find the focus.
I see. Okay.
So I've got two foci in my ellipse, and those points are right here and here.
So do ellipses always have two focuses?
Yes. Yep.
Okay.
So parabolas only have one, hyperbolas will have two. Okay. Let's do another one. Now it's kind of handy to have things in this form. And right now, this problem is not in that form. So what I could do with something like this is, let's see, 4x squared plus 25y squared equals 100. Because I want to get the 100 on the right-hand, or a 1 on the right-hand side, one way to do that is to divide everything through by 100. And that'll give me x squared over 25, which I can then write as x squared over 5 squared. So let's do that over here, x squared over 5 squared plus y squared over what? Can anyone do that? And then write it as a squared. 25 goes into 100.
2 squared.
Good, 4 times, and then 2 squared is 4, so perfect. So nice. With this, you should be able to easily plot some points. So how would that look? Well, in the y direction, to go up 2 and down 2. So let me put a couple points there. Up 2 and down 2. And then in the x direction, to the left 5 and to the right 5. So now it's time to play connect the dots. I missed. There we go. And last but not least, we need to find C. So C squared is going to be the difference of these two things squared. So 5 squared minus 2 squared. C is going to be the square root of 21. And I don't know exactly what that is. It's going to be 4 something. So 4.6. So, okay, 4.6. So in the x direction, start out at the center, move 4.6. It's going to be about there. And negative 4.6 is going to be about there. So that would have coordinates of negative root 21 and 0, and positive root 21 and 0. Looking okay with example E here.
I got a question.
Yeah, thank you.
Why previous one has the focus on the y-axis, x-axis, and this one?
Great question. So the focus is always going to lie along the major axis. The major axis is going to be the longer of those two. And so the longer of those two between here and here is going to be in the x direction. So that's your major axis. So whatever denominator is bigger is going to have to be your major axis, and that's where you're going to find your foci. Does that help?
All right, thank you. Yeah, thank you.
Okay, thank you. I'm not sure I'm going to bother to try and find the foci in this one, but I am going to help you whip it into shape. Now, with our last one, we divided everything through by the right-hand side to get 1, but I've already got 1 right here. So this one's going to take a little bit more finesse. And what I'll do here is I'll rewrite it this way. I'll write it as x squared over 1/9 plus y squared over 1/4 equals 1. Now, when you divide by a fraction, the trick is to invert and multiply. Now that I've got it written like this, I can think of that as 1/3 squared. And what else? 1/2 squared. And that'll equal 1. Now let's just verify that the graph that I've drawn seems to make sense. How far would I move in the x direction to find vertices? I gave you this and said, all right, label the vertices in the x direction here and here. Yeah, 1/3. And you can see, you know 1/3 is about 0.333. Well, that looks pretty good. It's a little bit to the right of 0.3, a little bit to the left of -0.3. So, yeah, -1/3 and 0, +1/3 and 0. And in the y direction, up 1/2, down 1/2. So points like this, 0 and -1/2, and up here, and 0 and 1/2. Hey, Liu, which one's going to be the major axis, the x-axis or the y-axis?
Y-axis.
Yeah. Cool. All right. So might as well finish this one up. If I'm going to find the foci, I'm going to calculate c squared equals, well, the larger of these would be the 1/2. 1/2 squared minus 1/3 squared. So that'd be c squared equals, if you get common denominators, that would be 5/36. So c would equal the square root of 5 divided by 6. Let's see what that is. Square root of 5 divided by 6. So about 0.37 something.
Wouldn't it be plus or minus 6? Or
Yeah, plus or minus. The plus or minus is because you could give us both points. So about 0.37, so somewhere up here, and -0.37 somewhere down here, both sides. How are we doing with ellipses here? Doing okay?
Yeah.
Okay, thank you. Let's move on to hyperbolas. Hyperbolas are kind of a neat shape. Not as many applications as the parabola that I'm aware of. There might be more, I don't know. But just a couple quick ones here. Some things to show you. So now the shape here of the parabola is really just the blue graph, the blue part of the graph, the two parabolic looking curves that face away from each other. The rest of the stuff is how we're going to graph it. So we're going to graph it by plotting the 4 points that you would if this were an ellipse. Then we'll draw this box through those 4 points. And then we'll draw the diagonals through that box. And that those diagonals frame the graph for your hyperbola. So that's going to be our approach. Some applications. Shape of a nuclear cooling tower is a hyperbola rotated around an axis. Before there was GPS, there was a system called LORAN, found you by intersecting two parabola hyperbolas on the surface of the Earth. Sonic booms, shape of the airport in Washington, near Washington, Dulles Airport has a hyperbolic shaped roof. Kobe Tower in Japan. So these ones, you know, the coins that roll in, I'm not sure if that's a hyperbola or not. So if somebody could tell me, that'd be great. All right, so let's graph some hyperbolas. Let's see. So hyperbolas. And we'll start out with 4x squared minus 9y squared equals 36. You might imagine that we're going to do the same thing here that we did with our ellipses, and that is to divide everything through so we have a 1 on the right-hand side. If that was your musing, then you'd be correct. So that would give me x squared over 9 minus y squared over 4 equals 1, which can be further rewritten as x squared over 3 squared minus y squared over 2 squared equals 1. And that's a good place to kind of get things rolling, is right here. Now, as I said, we're going to graph these things by starting out with what would be the points that you would graph if you were graphing an ellipse. But how do I know that this is a hyperbola and not an ellipse? That's an important difference. So can someone tell me that? Yeah, because of the negative sign. Remember, these two terms are opposite in sign, so it has to be a hyperbola. So let me put some points on here. Now, when you're drawing these things freehand, the one important thing that I would suggest is you try and make your points pretty evenly spaced. If you squish them in one direction and not another direction, then things won't turn out so nice. So let's pretend that this is an ellipse. If this was an ellipse, in the x direction, I'd start by plotting points where? Where on the x-axis?
3 and -3.
Good. 3 and -3. Great. Now in the y direction, well, I'd plot them at 2 and -2. There's a difference here. Maybe if you want, you put a little hollow dot. Because the x squared term is greater than 0, it's going to open left and right. The hyperbola opens left/right. If the y squared term was greater than 0, because if I didn't have that negative here, then it would open up and down. So these aren't exactly vertices. They would be the vertices that you'd be plotting if that was a plus sign and this was an ellipse. So that's exactly the 4 points that I'm going to work with. It's just that you've got to remember there's a minus there. This is a hyperbola. Now, let's play connect the dots with this stuff here. We're going to draw a box that goes through these points. So these 4 points are going to help us draw this rectangle We're going to get a lot out of that rectangle. After you draw the four corners, it's going to be the four sides of your box, then we want to draw the diagonals through the box. So let's do that. Now, none of this is yet the hyperbola. This is all just kind of like scaffolding. And we can see that I didn't draw my graph too accurately because these lines should be passing directly through the center. If they're really far off from the center, you might want to go back and look and say, well, wait a minute, am I doing this right? Once you draw these diagonals, they should pretty much hit the center of this. Now, the center of this first example is 0, 0. The next example that we'll do will not have a center at 0, 0. The idea with our graph here is that it's going to help us draw the hyperbola. I'm going to start out at one vertex and draw a line that gets closer and closer to my asymptotes, but never quite touches. Like that. And then I need to do the same thing over here. Here. Like that. And there's my hyperbola. Yay. There's one thing that's missing from this. Something that we found for our previous two conic sections, we're going to have to find for this one. Can anyone make a suggestion as to what's missing?
Focus.
Yeah, the focus. So let's assume that you have a hyperbola that looks like this or this. Either of these are hyperbolas. Both of them have the same center at H and K. But the focus lies a distance of C away from the center inside each branch of the hyperbola. Hyperb, yeah, it'd help if I could spell. Hyperbola. So you might ask, how do I calculate C? C is going to be A squared plus B, or C squared is going to be A squared plus B squared. So that's how you're going to get C, is from this relationship. A and B are just going to be your denominators. This is really close to what other formula? Looks very close to your formula for an ellipse, right? Now here's the thing. If you use the wrong formula, your foci are going to end up in places that you don't want them. If you use the wrong formula for the ellipse, then your foci are going to land outside of the ellipse. That can't happen. Conversely, if you use the wrong formula here, your foci will end up inside the hyperbola. And that can't happen. Your foci should be out here and out here. So probably here and here, I'm guessing. We'll calculate that. Let's actually find out. So, oh, you know what? My guess was wrong. I can tell you that right away. So c squared is going to be 3 squared plus 2 squared, which is 13. Square root of 13. It's going to be 3 and change, or yeah, 3 and change. For some reason, I thought we had numbers of 3 and 4. All right, so about 3.6. Now the 3.6 is just for our own sake, so that we know about where to graph it. 1, 2, 3. Now it should be between 3 and 4, probably a little bit closer to 4, so about there. Now you can label it with the correct coordinates though. It's going to be square root of 13, comma 0. And then another one over here at negative root 13 and 0. That's a pretty good description of this hyperbola. I guess there's one more thing we can do. And it's kind of a shortcut. It's kind of a cool shortcut, really. I don't think you're going to find this in the book. I almost feel like stopping the recording because I'm sure that some of my colleagues would object to my little shortcut here. I did justify it to myself once, but only once, and I'm not going to justify it here. Suppose you want to find the equation of these lines. It's not that hard in this case. I mean, you can just count over and count up and you can be done. But I'll show you a trick that works for me. Maybe you'll find it useful as well. But because this line gets really, really close to this asymptote, it's as if the difference between these two was 0. And what I do is I take my equation up there and just put a 0 and then solve for y. So if I take x squared minus, or over 3 squared minus y squared over 2 squared equals 0, and then solve for y. Let's move that to the other side. X squared over 9 equals y squared over 4. Multiply both sides by 4. I get 4x squared over 9 equals y squared. If I take the square root of this, square root of 4 is 2, square root of 9 is 3, and then I'll have square root of x squared is just x. I'll end up with plus or minus 2x over 3 equals y. And that happens to be exactly my two asymptotes. So this would be y equals 2/3 x. This is y equals negative 2/3 x. There. When you study physics, you might study a Carnot engine, which is a theoretical way to calculate how much work and energy goes into and comes out of a system. And at one point, in analyzing certain figures, you might be looking at the difference in the area between two hyperbolas to figure out the maximum efficiency possible for a particular engine. Your furnace at home might be a 90-10 or a 95-5. When I grew up, they had 80-20s, but that's the efficiency. Now, the efficiency is not compared to the energy you put in, the energy you get out. It's compared to the possible maximum efficiency that you can get from any such system, which is only about 64%. So you're getting 98% or 90% or 80% of the 64%. But that's for your physics class, not here. Any comments on the hyperbola here? We're going to do one more hyperbola. This time we're going to have something without a center at 0, 0. So I think this one was one from your book or from WebAssign. It certainly is not a problem that I would write. Oops, it'd be a minus there. 5/16 x minus 6 squared equals 1. Now right away, we're kind of running into the same problem that we ran into earlier with, I think, one of our ellipses, and that is you want to write these as things that are over 1. So if I multiplying and dividing are pretty close to each other. So if I divide by this reciprocal of this, that'll give me something equivalent to what I have. Because when you divide by the reciprocal, that's like multiplying by the reciprocal. X minus 6. So what should I write here? What should I put in this denominator?
16 over 5.
Thank you. 16 over 5. And then I want to rewrite that a little bit more. I want to write this as squared terms. So y minus 2 squared over 2 over the square root of 5 squared minus x minus 6 squared over 4 over the square root of 5 squared. And the reason I want that is because I want to figure out what my A and my B are in this particular problem. Now, despite the fact that these are kind of ugly numbers, overall the problem will work out okay. It might be handy to figure out just what these numbers equate to. So I can take 2 divided by the square root of 5 and get about 0.9. So 2 over root 5 is about 0.9. And a quick way to get this one is just to take this and double it, right? So times by 2, okay, about 1.8. 4 divided by the square root of 5 is about 1.8. Okay. Let's do something else while we're here, and that is find the foci. So for this calculation, I need to calculate c squared equals a squared plus b squared. And I think you might be pleasantly surprised here. C squared is going to be 2 over square root of 5 squared plus 4 over square root of 5 squared. So it's going to be 4 over 5 plus 16 over 5, which is 20 over 5, or 4. Okay, so C is plus or minus 2. Well, at least something worked out nice and even in this problem. Not that much else did, but that's okay. Now there is something different about this one, and I chose this problem in particular for that. And that is this part right here, or you can see it here. Which way does this open? Up and down or left and right?
Up and down.
Thank you. Opens up and down. All right.
How do you?
Somebody said, how do
How do you know that it opens up?
if the y squared term is positive, then it opens up and down. If the x squared term is positive, it opens left and right. So, for example, in our last one, the x squared term was the positive one. When we got things into a nice, neat form, get a positive x squared, a negative y squared. So this one's going to open left and right. If your y squared term is what's positive, then it's going to open up and down. Does that help out?
Yeah.
Okay, good. What's the center on this one?
2 and 6, or 6 and 2. Sorry.
Ah, nice, nice. I'm glad you caught that, because I mean, we're used to just reading these things off. It's like, okay, 2 and 6, but oh, wait a minute. It's the x coordinate that's 6 and the y coordinate that's 2. So 6 and 2 would be your center. So we'll start there on our graph. Let's see, 6 and 2, let's go from left and right, oh no, up and down. All right. So I'm trying to draw it, giving myself room to fit in here. Four. So let's start by graphing our center, which is at 6 and 2. Then we had points above and below that by about a distance of 0.9. So right here and right here. So points above and below. And then to the right and to the left. So a distance of 1.8. So not quite to 8, not quite all the way down to 4. So kind of tiny. So again, in the y direction, you went up by this much and down by that much, which is about 0.9. To the left by 1.8 and to the right by 1.8, corresponding to the approximate decimal value there. That gave us these 4 points of the compass, north, west, east, and south of our center. Let's draw a rectangle through these points. Now these points would be the points that you would be drawing if you're drawing an ellipse. But this isn't an ellipse because I've got a minus sign between these two. So it's a hyperbola. Don't mess that up. If you mess it up, there's not much partial credit you'll get. You might get the center right, all right? But if you're drawing an ellipse versus a hyperbola, there's not much partial credit I can give you. So they're just that different. So draw the diagonals. Once again, let me note for you that when you draw these diagonals, it should go pretty close to right through the center of that box. if you made a mistake and you went too far in one direction and not in the other, or vice versa, then what you'll see is that these diagonal lines don't meet in the center like that, like they're supposed to. This one opens up and down. So draw a nice smooth parabola that gets close to but doesn't quite touch these asymptotes. Now, if you happen to touch it just a little bit, that's not a big deal. The only thing I'm looking for is that you don't just bounce off of it. Don't curve back in, because it's not like a pool table or anything like that. It doesn't ricochet off. This shouldn't come back in. These stay infinitely close to the asymptotes. Now your foci are going to lie a distance of 2 up and 2 down from the center. Our center was at 6 and 2. So at 6 and 0, you're going to find a foci. And at 6 and 4, you're going to find another foci.
I'm confused. How did you find the, like, I don't know how to explain. The dimensions of the box, I guess? Like
Okay.
the top and the bottom?
Good question. So the top is this distance away from the center, up and down. Now, I calculated an approximation to that value as about 0.9. So I calculated that just for my own convenience. So I said, okay, about 0.9 up and 0.9 down. Likewise, over here, the distance as you find those points is going to be about 1.8. That's just the numerical value here. So you're going to start out at 6 and move 1.8 to the right, and start out 6 and move 1.8 to the left. So that's where I got these points here, upon which I drew the sides of my box and then drew the diagonals there. Does that help? Is that what you're looking for?
Yeah.
Good. Is there anything else on this one? You could, kind of like the last one, set this equal to 0 and find the equations of the asymptotes. It'd be kind of ugly on this one, but it would work. It actually give you the equations of the asymptotes. Pretty nice. I'm kind of conflicted. You want to see that? All right. Let's just knock it out for sake of completeness. So I'm going to go back up to the top equation here and work with that. You know, yeah, it doesn't matter. I guess if it works with this one or this one, I'll just work with this one. So y minus 2 squared over 4/5 minus x minus 6 squared over 16/5 equals 0. Remember, we're replacing that 1 with a 0. If I move this term to the right-hand side, I'm also going to take the reciprocal on this, so it's going to be 5 times y minus 2 squared over 4 equals 5 times x minus 6 squared over 16. We're going to solve for y. So I'll divide out the 5 on both sides. That'll disappear. So that's nice. Get rid of that. And then multiply by 4 on both sides. So I get y minus 2 squared equals 4/16 x minus 6 squared. If you're dying for me to simplify that, sure, got your back. y minus 2 squared equals 1/4 x minus 6 squared. I got an extra parenthesis in there. That'd give you a computer error. I'll overlook it. If you take the square root on both sides, you get y minus 2 equals plus or minus square root of that. It's going to be 1/2 x minus 6, no longer squared. Move the 2 to the right-hand side, y equals plus or minus 1/2 times x minus 6 plus 2. That would be the equation of each of your asymptotes. You can clean it up from here, but I think that's a good place to leave it. Asymptotes. Okay, anything on hyperbolas here? All right. Wonderful place for a break. See you in a few minutes.